Hello, and welcome to my presentation. The topic I chose to talk about is a cornucopia of metrics on Rn. In particular, I'll be talking about the subset of possible metrics that one can define of this form. Given 2 points for each component, you raise the difference to some power, and then take the inverse power for the sum as a whole. Over the course of the 5 minutes, I will mention a pair of familiar examples and look at the possible bounds of the power. Perhaps the most familiar case for us is the D2 metric, where we take the square root of the sum of squares. It is known as the usual metric on Rn. As an example, here's what the ball for D2 would look like in the space R2. As you might expect, the result is just a circle, where the radius of the circle is the same as the radius of the ball we are trying to find. Another familiar case for us is the D1 metric, where we just add up all the differences in each dimension. It is sometimes called the taxicab metric, since it measures distance only parallel to axes, similar to a taxi traveling in a grid-like city. Here's what a ball looks like for the D1 metric in R2. As you might expect, it looks like a diamond, because this is the shape that preserves the sum of the horizontal and vertical distances to the edges. Now we move into the more interesting material, considering the upper limit on what is possible. You may recall from the lectures that d infinity is defined in this way, but it is helpful to understand why this behavior happens, since we don't see a sum or a power and don't recognize the formula from before. Here's what we want to prove. For simplicity, let us call the maximum here m. We can identify the upper and lower bounds on the value of d for an arbitrary power. A lower bound is that we ignore all terms in the sum except for the largest one. An upper bound is that we set all the terms equal to the largest one. Re-expressing these bounds and taking the limit, we find that both the upper and lower bound end up being m. Consequently, the limit of the metric is m as well, as desired. As before, taking a look at a plot in R2, we see what we might expect. For small powers of p, we get the metrics from before, but as the power approaches infinity, we get a square, where half the width of the square is the radius of the ball, in this case 1. Now, we must identify the lower bound of the power. Here are the 3 cases for what p can be, given that it is less than the aforementioned p equals 1 metric. For negative values, even if we work around problems with division by 0 using infinity, we run into a problem where distinct points have a distance of 0 between them. Since we should only have a distance of 0 between a point and itself, these powers cannot define a metric. For p equal to 0, ignoring strange behavior with 0 to the power of 0, we run into having infinity be the distance between all points, which obviously fails to be a proper metric. For p between 0 and 1, however, the problem is a bit more subtle. Consider these 3 points in Rn, where the first is the origin, and the other 2 are 1 away from it. The distance from the origin to the other 2 points is obviously 1, no matter the power in the metric used. The distance between those other 2 points, however, depends on the metric. If you do the math, you end up with a value of 2 to the power of 1 over p. According to the triangle inequality, the distance between the 2 points must be at most equal to the sum of the other 2 sides of the triangle formed with the origin. This can only be true when p is greater than or equal to 1. So we already knew the lower bound as the D1 metric and just haven't proven it yet. Let's take a look at the 3 cases visually. First, we have the negative numbers. As you can see, the ball ends up being infinite in the 2 directions along the axes. And this represents how when even one coordinate is shared between the points we are trying to find the distance between, the distance ends up being 0, as you can see from this formula down here. When the difference in x is 0 and the difference in y is 10, you get a distance of 0, which shouldn't happen unless both of the values were 0. Next, if you try to plug in a power equal to 0, you don't get a ball, which is exactly what you might expect, since earlier we mentioned that distances with p equal to 0 are all infinite, so a ball of finite radius would contain no points. Finally, for powers between 0 and 1, we get this, which looks promising, but the way that the diagonal works out to be, it's way too short, and the triangle inequality fails because of it. In conclusion, this formula defines a metric on Rn for p between 1 and infinity, inclusive. Unfortunately, due to the time constraints of the presentation, I couldn't talk about some important things that you should still consider. First, it is still left to prove that these formulas actually abide by the triangle inequality, since I only showed that other values of p don't. Second, there is a relatively clear relationship between metrics with different powers, where larger powers measure smaller distances, for which the proof is quite interesting. Thank you.